3, 2.
In this circuit, we have a series circuit calculating voltage drops in it. We have 3 capacitors in series. We have a 20 microfarad capacitor, a 25 microcapacitor, and a 45 microcapacitor. 440 volts at 60 hertz. Now the formula for calculating voltage drops in any circuit is always going to be Ig times the resistance, X of C. But before we can do that, we need to calculate total capacitance, and we need to calculate the capacitive reactance of each one of these components. So to find total capacitance in a series circuit, it's the opposite of resistance in series. So we have to do the reciprocal in series for finding capacitance. So 1 over C1 plus 1 over C2 plus 1 over C3. So it's the reciprocal method. So 20 reciprocated plus 25 reciprocated plus 45 reciprocated. You hit enter and reciprocate it one more time. Gave us a value of 8.91 microfarads. Now, every capacitor in this component was in microfarad. So we can keep it in its value of microfarad because the outcome will be in microfarad. Okay, so that's how we calculate total capacitance. Now the next step that we had to do was calculate capacitive reactance in this circuit for each of the capacitors. Now it's still the same formula, 1 over 2 pi f of C. So to find the capacitive reactance of X of C1, it's 1 over 2 pi FC. Put the values in it. Don't forget to put the 20 times 10 to the power of -6 in it, and it gives us a capacitive reactance of 132.629 ohms. Same formula for the second capacitor, 1 over 2 pi FC. Plug in the values, gave us an outcome of 106.10 ohms for X sub C2. Capacitive reactance for the third capacitor, same formula, does not change. Plug in the values, gave us a capacitive reactance of 58.94 ohms. Now we have all the values for the capacitors and capacitive reactance. In a series circuit, these values are in ohms, so they just add up like any other series circuit would be. So total capacitance, X of sub C1 plus X of sub C2 plus X of sub C3. Add the values that we got, the 132.629 plus the 106.10 plus the 58.94 gave us a total capacitance in this circuit of 297.67 ohms. Now, in order to find voltage drops, we have to know what the current is in this circuit. And since it's a series circuit, current stays the same through all the components. We know what the total voltage is. The total voltage was 440. And we have the value of the capacitive reactance, the total. So the total current is equal to the total voltage divided by the capacitive reactance. So 440 volts divided by 297.67 gives us a current flow of 1.478 amps. Now that we have the total current flowing in the circuit, we can calculate the individual voltage drops. Coming back over here, the voltage drop across the first capacitor using the total current, 1.478, times the value of the capacitive reactance of 132.629 gave us a voltage drop of 196.03 across the first capacitor. Same formula for the second capacitor to find the voltage drop. Total current times the capacitive reactance of the second capacitor. Plug in the values, 156.83 volts. For the third voltage drop, same formula, total current times the capacitive reactance of the third capacitor, 87.128 volts. Now, you want to double check yourself to make sure this is correct. Add them up. Voltage drops in series are additive, just like they are in DC resistance or inductance. So the total voltage is equal to EC1 plus EC2 plus EC3, and I rounded them off, so 196 plus 156 plus 87 gives us our 440 volts, which is the voltage that we started off with, and that's how you calculate voltage drops.